Okay, part B. Oh yeah, this is a fun demonstration. When an alternating voltage is applied across a coil wrapped around an iron core, like that, an aluminium ring around the core will float at some height above the coil. So here's our ring. Aluminium, not magnetic, it's going to float. Quite a simple question. Explain why this happens. Okay, so what we need to think about is what's happening with our electromagnetic fields. So you've got an AC source, coil, that's going to, immediately the things I'm thinking, well, AC source, well actually current around a coil, current in a coil is going to generate the magnetic field, B field. Okay, and this is an alternating current. So what we've got is then an alternating B field. Therefore, so we've got a B field that's going to go around like that, something like that. And with the AC current, that's sort of kind of go in and out. So that means lines of flux are moving. Lines of flux are going to be cut by this ring, which is going to induce a current around the ring. So kind of, let's draw B field out a bit more. So it's actually cutting a ring. So alternating current, so it implies alternating B field, which implies lines of flux cut by the ring. So these sort of lines sort of move in and out of the ring. Faraday's law, flux being cut by the ring, it means there's going to be a potential difference induced around the ring. Potential difference, aluminium is a good conductor, you're going to have current flowing. Let's knock some current on. Now, how does it flow? There's obviously a force, there's got to be an upward force on the ring. So if you've got a current flowing, then again that's going to generate its own magnetic field. So ring generates B field. So that one is going to have its own B field around there. Let's draw that as a solid line. Now we can be sure that when you've got one magnetic field inducing another one, they're such that they repel each other. That's Lenz's law. Implies this B field repels the first one, or acts against the first one. Therefore, you've got a force of repulsion between the coil here and the ring here. your repulsive force, and I guess you could take it one stage further and say, why does it float at a particular height? That's where the force of the repulsion balances the force of gravity. So as this thing goes up, the force of repulsion between here and here is going to go down, and at some point it's going to exactly balance the force of gravity. So it floats at a height such that the force due to the B field equals mg. That's the mass of the ring. What I haven't commented on, which I think I should in the answer, is this iron core. What the iron core does is increases the strength of the magnetic field. So it brings a strong magnetic field up through the core. So that means that although the ring is down here, you've still got a very strong magnetic field up through here. So perhaps a better diagram would be where the magnetic field from the coil looks more like that, because it's being channeled up through the iron core. Of course, when you're answering the question, they've conveniently sort of drawn it for you, so there's no reason whatsoever why you can't draw on that diagram. So we can do that. And I think that explains the answer. Explain why this happens. Why is this aluminium ring floating? I've got the force of gravity is balanced by the magnetic repulsion. The key things are the current and the coil is generating magnetic field through the coil and the core. It's an alternating current, which means these flux lines are moving in and out. They're being cut by the ring, the voltage around the ring being induced, which means the current flows around the ring, generates its own magnetic field. You've got the repulsion. So there's a lot of steps in that, but that's basically your electromagnetism. And having done this experiment a lot in the lab, although the question doesn't answer it, ask for it. If we put a hole in that ring, it doesn't work, it doesn't go anywhere. That's because your current can't flow through there, so you don't get this second magnetic field. If you really want this to go really well, you cool a ring in liquid nitrogen to start with, so that lowers its resistance, which means more current flows for the same voltage. You get more B field and more repulsion. Up it goes, and if you get it right, it hits the ceiling. Okay, so that's why it moves. Again, with that sort of explanation, I would write it out on scrap paper, first of all, to make sure you've really got the steps right before you try and put your words down on paper, so it doesn't come out messy and not jumping around all over the place. You don't miss a step out.
It seems to me that this is the sort of open-ended question that an examiner would use to differentiate between marks between multiple students who might be at a similar level.
Yeah.
It's this question you can get into more detail if you need to.
I mean, you could easily say, okay, we've got an alternating current there, it's a transformer, therefore we've got a B field there, which is right. Then this goes through step by step, gets all that.
It's much better.
Points through there.